ওকে, এই লেকচারের রেকর্ডিংটা আপনারা ইউটিউবে পাবেন, আমি দিয়ে দিব। আর আপনার এটা পাওয়ার পয়েন্ট প্রেজেন্টেশনটাও আমি মেইলে পাঠিয়ে দিব। সুতরাং আপনাদের খাতা কলম নিয়ে নোট করার দরকার নাই এবং খেয়াল করেন জিনিসটা কি বলি। আচ্ছা, তো আপনাদের টপিক যেটা সেলুলার ইনজুরি, অ্যাকচুয়ালি ইটস এ ভেরি বিগ টপিক, and we will not only have to cover the injury but the associated things as well, like cell death and aging. So we do not have much time for that, and it's actually spans 3 lectures, but let's begin anyway. So here you can see a spectrum of changes that gives a continuum from physiology to pathology. In undergrads, like while you were in MBBS, you might have heard something that whenever something is not physiology, it is pathology. But that is not strictly true, because it's very, very difficult to delineate sometimes where physiology ends and where pathology begins. There is no man's land in between physiology and pathology. So if anything is deviated from physiology, it automatically do not become pathology. And in physiology we do have some patterns, we do have some mechanism, we do have some feedback loops. There are some patterns of how normal things work. But if you think that since pathology is a study of abnormal, it doesn't have any pattern, that is wrong. Just like normal things have pattern, abnormal things also have got its own pattern, and we study those patterns in pathology. And there are some overlapping between physiology and pathology, and that there are some things which is neither physiology nor pathology. So it's like a shed. You cannot delineate where this white part of the shed is the mouse pointer visible? Is the mouse
Yes,
pointer?
sir.
Okay. So you see, I have marked the physiology with white end, pathology with red end. But can you tell exactly at which point this white becomes red? Here, here, perhaps here, or maybe here. Actually, there is no a single point to point at. It's a continuous process. Now, cells reside in a physiology, and the standard model is like that. When it encounters some stress, it undergoes some kind of adaptation, and these adaptations are many kinds of adaptations, but we generally speak of 4 types of adaptations: atrophy, hypertrophy, hypoplasia, and metaplasia. But we are not going to discuss cellular adaptation here. It's a lecture of its own, and your topic doesn't include actually adaptation. It starts from injury. So when adaptive response, it could be physiological or it could be pathological, hence the overlap, no man's zone I was talking about. Anything that is not physiology is not automatically pathology. Anything that is not pathology is not automatically physiology. There could be some in between. These adaptations are something like that. These are mostly reversible processes, but still it can be pathological. However, these cells facing stress first will go under adaptation, adaptive changes. It will atrophy, it will become larger, hypertrophy, it will increase in number, hyperplasia, or it will be replaced by some other differentiated cell type, that is metaplasia. These things might or might not help the cells to face the stress. If the problem is solved by adaptation, then it will not proceed any further. But if adaptation is not enough, or the stress or the stimuli that cause this adaptation, it persists even after the adaptation takes place, then the cell become injured, and we call it the reversible injury. a reversible injury is beyond adaptation. That some damage has been done, but the damage can be recovered. It can go back to normal. So hence it's called reversible injury. But even after the reversible injury, if the injurious stimuli persists, or the changes are not enough to cope with the stimuli or stress, then the cell proceeds into zone of irreversible injury. And irreversible injury by definition will end in death. So irreversible injury is like dead man walking. It's like irreversible. The cell which is irreversibly injured is like a person with capital sentence. Someone has been sentenced for death penalty, and just walking, a dead man walking, kept in condemned cell, is going to die in a designated period of time. Um, Either by hanging or in firing squad or in electric chair. But irreversible injury means a cell that is destined to die within a short period of time. It cannot go back to normalcy. So this is a outline of the general spectrum, that adaptation, reversible injury, and then irreversible injury, and then death. And in the process, the cells can have some intracellular accumulations. It's a byproduct of different metabolic processes, actually, but its origin is not always metabolic, and it can show up at different stages of cellular adaptations. Uh, but we will be mostly focusing on injury from now onwards. So I discussed this only to highlight the continuum or spectrum of changes that can occur in a cell under stress or pathologic stimuli, or in some cases physiologic stimuli as well. Now, what is cell injury? Cell injury results when the cells are stressed so severely that they are no longer able to adapt. That means it's past the adaptation point, no longer able to adapt, or when the cells are exposed to inherently damaging agents. So the cell can be injured in basically two ways. One is that it tried to adapt, did some sort of cellular adaptation, but that was not enough to combat the stress, or it was such a sudden blow, like hit by if someone is hit by in a road traffic accident, the cells will not have time to adapt. Even before it knows anything, it becomes injured. So sometimes there is persistent stimuli that causes cell injury after adaptation fails. Sometimes the injury is so sudden and severe that there is no time for the cell to adapt. It directly gets injured. So the cells are exposed to inherently damaging agents or suffer from intrinsic abnormalities. And there are some other abnormalities that can be inherently damaging the cell, which is preventing it to undergo adaptation, or favoring the pathways related to cell injury. So all these things ultimately boils down to one thing, that is a cell injury. So do you understand the discussion so far? If you have any question or comment, you can ask directly, or you can write in chat box, which I will reply later in the lecture. Do you understand the discussion so far? Hello?
Yes, sir.
Okay, thank you. Now, what are the differences between reversible and irreversible injury? So in reversible injury, I have already told you a definition that reversible injury can be reversed, hence it's reversible. It kind of seems a circular argument that the injury that reverses is reversible. So is there any way to go around that? Like, where do you live? I live with my parents. So where do your parents live? They live with me. So actually this doesn't tell us much about the actual location of that person. So, like that, if we just define that reversible injury is something that can be reversed, it is by definition a tautological argument. Means it comes returning back to the same thing, and we really do not gain much insight that what are the features of reversible injury. Because if we have to wait and see whether this injury goes back to normal, then the definition is not of much use. We have to have some criteria to find out that if this injury is going to get reversed or not, even before it gets reversed. So what are the things that differentiates between reversible and irreversible injury? So here, as an example, we see normal renal tubule, and in the middle panel, you see the reversible injury. The effects are cells have become swollen, the cytoplasm has become more pink. I mean, the protein has is more concentrated here, and there are some granular appearances inside the cytoplasm in some of the cells, and the nucleus is also a bit changed, but the overall cellular structure is there. The cell didn't burst, so it's not something like that. But in irreversible injury, it looks like the cells have so much swollen. Some of them lost its nuclei, and some of them just burst open. So a burst cell cannot form back into a whole cell again. So uh, these are visible features that tell us that this injury may reverse, but this one cannot. So these are some things we need to identify under microscope when we study different slides, whether it's reversible or irreversible injury. Now, there are other ways to highlight different injurious stimuli, but mostly if the mitochondria is damaged or the membrane is damaged, in that case, the injury is usually irreversible. Once the mitochondria is damaged and it's leaking, it's losing its contents, the membrane, not only the cell membrane, but also other membranes like lysosomal membranes, when these things gets damaged, then the cat is out of the bag. You cannot put it back inside. So reversible and irreversible injury is a continuous spectrum, but when it reaches to a point where the mitochondria or the membrane, cellular or subcellular membrane, those things are damaged, is probably you should not hope for the best. In that case, you have nothing to do. It will go towards the end, the death end point, that is death. So this is a shorthand to remember how to differentiate reversible from irreversible injury. All other kinds of things, if the mitochondria and membrane remains intact, the other things can reverse. But if you damage these two, it usually do not reverse. Now, what could cause cell injury? There are multitudes of causes of cell injury, as you can see here. But sometimes it is divided into extrinsic and intrinsic factors. Although there are overlaps, there are always overlaps. But even then, we can roughly say that hypoxia, immunological reactions, and genetic damages. These things are something that actually might be inside the homeostatic environment, as inside the milieu of the cell, I mean the internal environment. So these things are probably something that is intrinsic factors that causes cell injury, and physical or chemical or radiation hazards, infectious agents, nutritious nutrition functional factors, those things, including the oxygen level, it can fall into both intrinsic and extrinsic factor categories. So these things can cause cell injury in various ways. We don't have time to go into the mechanism for each of these. We will just have a general overview. Now, the hypoxia, it's one of the most important and versatile mechanism of cell injury. The, hypoxia is a setting that as in clinical practice, we face time and again. It's a very common form, a common agent of cell injury. Now, uh, hypoxia occurs when oxygen need surpasses oxygen availability. Now, it could be a problem at different levels. The environment can have less oxygen, like in high altitude, or maybe some place where the oxygen level is low. So it can be at the level of the environment where the person is breathing. It can also be in the level of the person's own body. Maybe the heart is not pumping enough. Maybe some heart is pumping, but some of the tissue is not getting enough perfusion. These sort of things. So in this case, the problem is at the systemic level, and sometimes the heart and cardiovascular system, that is functioning well and good. Environment has got a lot of oxygen, but the cell cannot utilize it, maybe due to some poisoning, like some cyanide poisoning that blocks respiratory chain. So now it's at cellular level. So it can happen at different levels, but the thing is that the main point is that the oxygen need is surpassed. It's greater than the oxygen availability. There is a problem of supply and demand. So, and anoxia means there is no oxygen. I mean, no oxygen in blood whatsoever. So this usually do not happen. Mostly we deal with hypoxia. Anoxia can happen if blood circulation is completely cut off for some time or something, in some cases. But mostly we will look at injuries with hypoxia. And there are some fundamental differences between hypoxia and anoxia at cellular level. And these details are actually not in this scope of this lecture. Having a little bit of oxygen, what do you think? Having a little bit of oxygen is better or worse than having no oxygen? Is anyone? Uh, Anyone, whatever you think. I'll not highlight on this much further. Just I want to listen to what you think. Nobody is interested. Okay, that's a shame. Now move on. Now, what could cause hypoxia or anoxia? So there are many factors, as you can see. It could be high altitudes. It could be due to drowning. Could be some lung parenchymal diseases or interstitial diseases. Could be a problem in the heart or cardiovascular system, or maybe the oxygen transport is defective. So there are different causes of hypoxia or anoxia. So I'll not bore you with a long list. I'm just giving you a basic idea of it, and your textbook has got the list. And now the thing is that I'll be focusing on how hypoxia, however may it be caused, it causes cell injury, right? So how does hypoxia cause cell injury? So the general mechanism is like this. If there is ischemia in a tissue, maybe due to a blood clot or something, thrombus, whatever. So whenever tissue perfusion is reduced, the mitochondria is getting less oxygen. The oxidative phosphorylation stops or reduced, which causes the reduction in ATP synthesis. Now, when ATP synthesis is reduced, the ATP dependent processes gets halted, like sodium pump, sodium potassium pump. These mechanism stops, and ribosomes are detached from uh, endoplasmic reticulum, and the ribosome mRNA complexes, they also get detached from one another, because protein synthesis is an energy consuming process. No ATP, no new protein, only degradation. So this is the thing. Now, and in the absence of ATP, the anaerobic glycolysis takes hold. It gets upper hand. And anaerobic glycolysis causes glycogen depletion because it has to have a huge amount of, has to get a huge amount of glucose from somewhere. Because it's less efficient, it needs more glucose to produce the same amount of ATP as would to compensate for the oxidative phosphorylation in aerobic glycolysis. So the glycogen levels are depleted, and anaerobic glycolysis cannot get rid of lactic acid, so the pH falls, and low pH causes all kinds of problems like clumping of nuclear chromatin is written here, but all other kinds of problems are also take hold, like lysosomal membrane activation. We'll get to that later, but for now just keep in mind that low oxygen causes low pH in the cell. So here's some mechanisms clumped together here, aggregated together to show like how does the ATP deficiency causes cell swelling. So if that question is asked, then the answer will be just this highlighted portion, that ATP production is reduced, sodium pump is written here. Actually, they mean sodium potassium pump, but somehow they felt that writing a potassium will cost a little bit of ink, so they omitted it, but you should probably write sodium potassium pump. Now, the sodium potassium pump stops functioning, and what would that do? It will create actually an efflux of calcium outside the cell, but and even more sodium will be retained inside the cell. And as sodium is retained inside the cell, and more sodium will actually come inside the cell as well, because extracellular sodium concentration is higher, and if no energy dependent process is going on, the passive diffusion will cause the extracellular sodium to come into the cells, because inside the cells sodium level is kept lower by the activity of sodium potassium pump. If it is stopped, then sodium channels will take over. The sodium channels will accumulate lots of sodium, and with sodium comes water, and that's why the cell will swell. And not only the cell, all the things that have membrane inside the cell, the subcellular structures like endoplasmic reticulum, the Golgi body, the vacuoles if there is any, and mitochondria itself, everything will get swollen. And this is how ATP deficiency causes cell swelling. And if it's asked how cell compensate for the loss of aerobic respiration by anaerobic glycolysis, what's the outcome? The pH will become lower, and protein synthesis is also diminished. So the cell under stress, if it needs to make some kind of protein to combat that stress, but cannot do that because they don't have ATP. So this is a vicious cycle, as you can see. Now, the water accumulates at different parts of the cells during cell injury. So, and it causes, the change it causes is called hydropic change, because hydro is water, and it's due to accumulation of water. So it's hydropic changes. So it can involve different structures, as I said. It can involve mitochondria, rough endoplasmic reticulum, and some new vacuoles can form, hypoxic vacuoles. Due to some super tiny structures get swollen, which is normally not visible. Those become hypoxic vacuoles. Now, these are all electron microscopic findings. In light microscopy, the usual microscope that we use day to day, we cannot see the subcellular structures like the mitochondria, the endoplasmic reticulum. Usually, these structures are not visible under light microscope. It can be seen under electron microscope. In light microscope, we only see that cellular cell size has overall increased, and the cytoplasm seems a bit scanty. It's like it's diluted or something. It's more watery. It looks pale. Why pale? Because there's lots of water, but the corresponding protein concentration has not increased because protein synthesis has stopped. So it looks paler than usual. So these are the things we see as hydropic changes. Sometimes you also see vacuoles, uh, maybe fat vacuoles that will come later. So these are the things that we can see in light microscope. You do not see endoplasmic reticulum or ribosome or mitochondria under light microscope. You need electron microscope for that. Now, there's a important role of calcium in acute cell injury uh, that has to be mentioned separately. As we have discussed, the sodium potassium pump inactivation causes some changes, including a side effect, side effect that is influx of calcium. The loss of calcium gets into the cell, and also mitochondrial damage occurs, which releases calcium inside from inside the mitochondria. So this increased cytosolic calcium, it causes a havoc because calcium is a signaling molecule. It is required for signaling at different parts of the intracellular signaling pathway, and uh, uh, and this needs to be in moderation. Uh, if there is too much calcium, then these pathways will go haywire. Like calcium is required for activation of different cellular enzymes, especially those enzymes which degrade things like phospholipases that degrades phospholipids, proteases that degrades proteins, endonucleases that degrades nucleic acids, like causes nuclear damage, ATPases that disintegrates ATP. So all these things are all these things gets access higher level because now there is lots of calcium in the cell. So the calcium unleashes this monster of a variety of degradative cellular enzymes, most of which reside inside the lysosome. So this actually starts to degrade the cell from inside, and mitochondria is already producing less ATP. Now calcium has come, and whatever ATP had the cell the remaining ATP that is also degraded by activation of ATPases. So it's a bad news. It's a double bad news for the cell. So I hope you get the idea. So can you follow me? Because without looking at the audience, it's really difficult to assess whether you're getting the lecture or not. Some feedback would be good. So far, could you follow the slides or follow through my arguments?
জি স্যার বুঝতেছি।
Okay, thank you. So I have to take the class as per the protocol in English uh, because it has to be in such a way that the student from any background or country can understand the lecture equally. That's why I am using English because I do not know about whether all of you are from Bangladesh or not, and this is going to be uploaded on the YouTube. So it's better to have the lecture in English for a broader audience. But if you do have any problem, you may address that regarding the communication in English. Now, is the
Sir, it's nice to know that it will be কি বলে, it will place in YouTube, and sir, we are lucky that this conversation is happening in English. Um, More we practice English, it will be helpful to us.
Okay, thank you. I appreciate that.
Yes.
Now, let's go to the next part. In this part, we're looking at the role of calcium in acute cell injury. So, as a side note, this is not related to cell injury. As a side note, maybe an interesting fact. At least I found it interesting. Do you know that what is the uh, uh, original role of bones in animals? The skeletal structures. It provides protection, gives a structure. But when it first came into being during evolution, what purpose was it serving? At the why the organism suddenly uh, started to make tough structures using calcium salts? Why is that? Later, it became adapted to give protection and structure. But what was the initial advantage? That has driven the evolution of skeletons? Can anyone guess?
Don't
Anyone?
know, sir.
Okay, thank you. So
Disruption of cytoskeletal protein, sir.
not exactly. Calcium is actually where life first evolved in aquatic environment, and especially around the hydrothermal vents. I mean, natural rocks, where loss of calcium carbonate was there. So calcium was a readily available source uh, of signaling molecules. It was initially used for different types of signalings, and still our bodies used calcium as a major signaling molecules. It signals a lot of things. It signals the activation of different cellular enzymes. It acts as kind of second messenger. It acts in coagulation pathway. It's one of the coagulation factors, factor 4, you know that. And it also acts in skeletal and smooth muscle contraction, also cardiac muscle contraction. It acts sometimes in nerve conduction, although not as importantly as sodium, but nevertheless it has a role. Now, all these things are basically the signaling molecules. It was readily available when the simple unicellular organisms came into being, but later it was helpful to accumulate some calcium inside the cell, and in turn the mitochondria and endoplasmic reticulum became the reservoir or storage house for calciums, which could release calcium when needed for different signaling purposes. And at some point after in time later, when multicellular organisms evolved, the this calcium storage was naturally selected to serve another purpose, to build structure, which helped in locomotion and other things. So initially, it came into the biological world. This inorganic molecule came into the living world as signaling molecules, but now we recognize calcium is something that toughens and hardens things. So this is an interesting thing. I think some of you will appreciate the beauty of it. Now, the cytoplasm of injured cells, acidic or alkaline, we have already discussed that. Anyone, could you please answer that in an injured cell, the cytoplasm, is it acidic or alkaline? What do you think?
Acidic.
Acidic,
Exactly,
sir.
acidic. Now, we have already said this, that oxidative phosphorylation is reduced, which causes anaerobic glycolysis, which causes increased lactic acid, and that drops the pH. So what happens when the pH is dropped? The breakdown increase the calcium, and the calcium is already activating all those enzymes, and the breakdown of phospholipids and ATP, and that increases the phosphate level. So increases in phosphate level also increases the acidity. That means it further reduces the pH. Other than anaerobic glycolysis, the phospholipids and ATP are broken down. That also reduces the pH in addition to the lactic acid driven pH drop. And these low pH, it activates the lysosomal enzymes. The lysosomal enzymes are degradative enzymes. It breaks down things, you know that. And the and it actually deactivates other enzymes. This is a very interesting thing. In low pH, your other normal usual enzymes, they stops working. You know, I think you know that, right? Most enzymes stop work at low pH. We know that from biochemistry, right? Anyone
Yes,
unfamiliar
sir.
with this? Yes. But the lysosomal enzymes, they do not work at normal pH. They work in acidic pH. So a low acidic, a low pH or acidic intercellular environment will deactivate all other enzymes, but only activate lysosomal enzymes. So what will that do to the cell? The cell will be eaten from inside. It will be degraded from inside if the lysosomal membrane is damaged. That's why the membrane damage is one of the hallmark of irreversible cell injury. Now, we have already discussed that. Now we see the mechanism of it. Now, the reversible and irreversible injury. What line, I mean, separates the two. When does reversible cell injury stops, and when irreversible cell injury begins? So where is the demarcation line? As we have seen, that it's a continuous process, like a shade of two colors. It cannot be, we cannot define it with very much precision. No well-defined separation between the two. But the two factors, I've already mentioned it before, and now emphasizing it again, that two factors are most crucial for irreversible injury that is usually not present in reversible cell injury. This is the mitochondrial damage and membrane damage. Why? Because both of them becomes leaky. They leak out things, their contents. Mitochondria leaks out the calcium and other proteins that causes cell death. And membrane damage is if the plasma membrane is damaged, then cellular content is leaked outside. If lysosomal membrane is damaged, then lysosomal enzymes are unleashed and does a lot of damage inside the cell. So if the mitochondria and membrane or one or both of them gets injured, get damaged, gets leaky, then there is not much hope for that cell but to die. Otherwise, whatever injury a cell faces, if the mitochondria is intact, membranes are intact, then you can assure the cell that, Mr. Cell, you are going to be all right. Don't worry, just hang on there. But if these things are damaged, don't give the cell a false hope, it will die. Now, which mitochondrial changes are irreversible? Up to a point, the mitochondrial changes can even be reversed. As I said, that once it ruptures, when it's normal to is just swollen, hydropic changes are there. Up to this point, it can somehow get reversed. If the stress is gone, if other things are taken care of, it can go back to normal. But if it ruptures, then it cannot go back. So when the mitochondria or endoplasmic reticulum or other membranous structures inside the cell gets blown out, their membrane forms coiled structures. That's an interesting thing. It's called myelin figure. So this is something we can only see in which kind of injury, reversible or irreversible injury. The membranous structures like mitochondria, if it's burst, then its membrane has to go somewhere. So then the mitochondrial membrane will coil onto itself. It will form a coiled structure. It's not visible under light microscope, but it can be seen under electron microscope. So this myelin figure later accumulates some calcium, because there is already a calcium in there, I've already mentioned. And the myelin figures, they're basically phospholipids. So they're negatively charged, and the calcium is positively charged. So it will attract calcium and cause a focus of calcification. In dead tissues or injured tissues, we see calcification because there are negative charges that can attract calcium. And in injured cells, there are a lot of calcium there. We have already seen. So hence pathologic calcification. So if you see the myelin figure inside a cell, what kind of injury would it be? Is it reversible or is it irreversible? Anyone?
Irreversible, sir.
Irreversible. Good. Now, this is what a myelin figures look like. The damaged membrane folding up on spiraling on itself. The subcellular membranous structures. If they're ruptured, they forms these myelin figures. It's only visible in electron microscopy, not visible on light microscope. So frankly speaking, I've never seen a real myelin figure because I don't have electron microscope in my department. Okay. What are the signs of irreversible cell injury? Now, these are some features we have already discussed. The cell has to be leaky, and the nuclear changes will be there. pH drops, and nucleases will break down the genetic materials in it. and the detached ribosomes will be there. Some lysosome will be some lysosomal enzymes will be released as well, and everything will be swollen. The cell itself will be swollen, and the membranous structures within the cell will also be swollen. So all these things constitutes irreversible cell injury. Now there are nuclear changes which has not been highlighted so far. In cell injury there can be three kinds of nuclear changes. One is pycnosis, where the nucleus condenses into a very tiny space. This is called pycnosis. There can be karyolysis. The nucleus is shred into bits, so much so that you cannot see it under light microscope, as if the cell has no nucleus. It looks like that. That's karyolysis. And the karyorexis is also when the nucleus is torn into small bits, but this time you can see it under light microscope. That is called karyorexis. Now, the clinical signs of irreversible cell injury, there can be many types of clinical signs. Like in MI, there is characteristic chest pain, chest tightness, fear of dying, breathlessness, etc. at rest. Also some kind of angina can also do that. All these things are cell injury. There can be some paralysis due to different types of injuries, and there can be ascites and portal hypertension. All these things can be seen clinically. And some metabolic diseases like in diabetes, it can be indirectly assessed by measuring the blood sugar level, so blood glucose level. So there are different ways to see the effects of cell injury. If enough of the cells get injured, the cumulative effect will show itself clinically. You cannot see it, the damage of single cell, but if lots of cell of a particular tissue or organ is damaged, then you can find it clinically. These are the clinical signs of irreversible cell injury. Now, when the cells are injured, their contents are released into bloodstream. So sometimes we can get intracellular enzyme levels to be higher in the blood to detect injuries of different organs or tissues. Like troponins, when cardiomyocytes are damaged, like in myocardial infarction or in some cases of angina, the troponin level gets high. Why? Because the cardiomyocytes are damaged, and these contents is supposed to be inside as a contractile element of the myocardial, cardiac myocytes, but instead it is ruptured. The cellular content is released outside, so it goes into the blood. And also some creatine kinase in case of skeletal muscle or cardiac muscles. Now the liver, if it is injured, then ALT or AST level will rise. Same thing, the intracellular enzymes will come outside of the cell and go into the bloodstream. Now, under normal conditions, if we measure all this, we get a zero value, or like will it be absent? The intracellular enzymes or materials that are used as markers of organ or tissue damage, like ALT, AST, CK, or troponin. In a normal person, will these things have a value of zero? What do you think? Anyone? Do you get my question? All these things.
Sir, repeat the question, please.
Huh?
Repeat the
Sir,
question, please.
no cell injury, irreversible injury. Reversible injury আছে কিন্তু irreversible injury নাই. Okay.
Well, there are baseline levels of all these things, because there is a normal cellular death and turnover happening all the time. So very tiny amount of intracellular materials are available in blood. So as a part of normal physiology, some cell death occurs all the time. So and some cell get burst open almost all the time. So very tiny amount of these things are available in blood. So there is the normal level is not actually zero. It's something more than zero. But once once the cells are a large number of cells are injured by some pathologic process, then the values becomes very high, and that's the abnormal range we usually detect clinically. Do you get my point?
Yes, sir.
Okay, thank you. But you're right. To get a lot of these into the blood, there has to be irreversible injury. That is correct. Now, there is another way that the free radicals can damage the cells. This is another way of cell injury. Now, what are the free radicals? So the free radicals are those which are hungry for electrons. If they get to some around some cells which has got some floating electron in its outer shell, it will grab that electron, and in the process, the healthy atom will become free radical itself, because then it will have the deficiency of electron. So then it will try to grab electron from another cell. So if the free radical comes into the picture, it creates other free radicals. This is a positive feedback loop. It starts. One free radical can generate thousands of free radicals, and those molecules will also become free radicals. They will amplify the process. So this is a very bad thing, free radical, and ultimately it will damage the membrane. It will damage everything. We'll look forward to it. But fortunately, there are other types of molecules which are called antioxidants. Okay, let's see what the common free radicals are, like the superoxide anion, hydrogen peroxide, hydroxyl radical, and peroxynitrite. These are the common free radicals, mostly oxidative free radicals, because uh, most of the time these are byproduct of oxidative phosphorylation. So oxygen is a really toxic element. I mean, agree or disagree? We are constantly taking in this
Sir,
poison to live. Huh?
agree.
Agree.
স্যার 100% যখন নিব তখনও তো ড্যামেজ হবে।
Okay.
আমরা তো
Well,
100% নিই না।
Well, when we take when hyperbaric oxygen therapy or 100% oxygen is given, the damage is greater. But under normal conditions, under normal oxygen saturations, uh, there is also free radical formation and damage to some extent, uh, because the mitochondrial oxidative phosphorylation process is not perfect. No biological process is perfect. So the oxidative phosphorylation process sometimes creates some unpaired oxygen radicals, which cannot find its corresponding protons to form water. Do you remember the oxidative phosphorylation process? At the fourth stage, at the fourth complex 4, there's supposed to be oxygen radical has to combine with 2 protons to produce H2O. That's the end point of the oxidative phosphorylation. Do you remember that step?
Yes, sir.
Okay. So the thing is, this process is basically quantum mechanical. It's random, and there is no 100% certainty that the oxygen will always find the 2 proton it's supposed to find and make water. So there is a certain percentage of oxygen, unpaired oxygen atom. This will go around alone, and whatever you do, you will not escape this. Under normal conditions, it also happens. Under hyperbaric or 100% oxygen concentration, it occurs more often. But under normal condition, it happens at low level, but it happens. Now, these oxygens, they combine with, I mean, if they cannot combine with 2 proton, it will form hydroxyl radical. If it combines abnormally, like H2O2, then it will create hydrogen peroxide. All these things will create some kind of problem as a free radicals, but free radicals are inescapable. I mean, we are breathing oxygen, and we're getting a lot of energy by oxidative phosphorylation, but as a byproduct, we are always creating free radicals. So this is part of aging process as well. So it's fair to say that with every breath we are dying a little bit. Okay. Do you get the point?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now, the oxygen free radicals are normally formed in the cells, but certain factors can enhance its productions, like radiation, toxins, reperfusion, etc. This enhances the production of this reactive oxygen species, and the biological systems has evolved to combat the deleterious effects of these free radicals using antioxidant mechanisms, as I've mentioned. But these processes are not 100% guaranteed to always make up for the damage the oxidative free radical has done. It cannot always 100% neutralize, but it tries. That's sure. It tries to do its best. Now, the oxidative free radicals are neutralized by a combination of different enzymes and free radical molecules, which also includes, among other things, vitamins A, C, and E. But there are other things like glutathione peroxidase catalase. These enzymes are also there. Basically, they are the molecules which can donate the electron to the free radical and neutralizes it. But these molecules, after donating electron, they themselves do not become unstable. The problem is when free radical snatches an electron from an adjacent molecule, that molecule becomes free radical itself. So it propagates, it amplifies. But in case of this special kind of molecules, they can donate electrons without turning into a free radical themselves. You can think of it like that. Free radicals are like, um, like, like zombies. If they bite some healthy person, that person also becomes zombies. But these antioxidants, there's something, they can kill those zombies without getting hit by the zombies. So you can think of it like that. Now, the pathological effects of free radical damages. So lipid peroxidation can occur, and it will damage the membrane. The protein modification can happen, like breakdown of the protein or misfolding. When the protein is misfolded, its function is lost because the structure dictates the function. If it's folded the wrong way due to free radical interaction, then it cannot do the thing it's supposed to do. So, and this misfolded proteins has got its own pathological array of problems, unfolded protein response. So that's another story. Now the DNA damages, it can cause mutations. Uh, so the free radical induced damages contributes to cellular aging. And best case scenario of such a damaged cell is cell death, a peaceful way to go. But worst case scenario is cancer because it can cause mutations. Now, cell injury caused by hypoxia or anoxia, can it be reversed by providing the cells with adequate oxygen? What do you think? If there is low oxygen, can we reverse the process by giving oxygen?
No, sir.
Why not?
No, sir.
Anoxia, sir, fibrosis will. Anoxia.
Okay. Well, the irreversible cell injury cannot be reversed, but even if it is in reversible stage, there can be ischemia reperfusion injury, which is most commonly seen in myocardial infarction cases where the streptokinase is given or PCI is performed, the circulation is established, the patient seems to improve, but suddenly the blood pressure falls again, and the patient goes into some VT, ventricular tachycardia, or atrial fibrillation or something. Suddenly gets worse. It first gets better and then gets worse. So this is something we have to keep in mind. Why? Of course, if you're perfusing with blood, then oxygen will also go with the blood. So there will be more free radical formation. Reactive oxygen species will be there. So it will the perfusion is re-established, but that perfusion can itself cause the damage. So one reason is this reactive oxygen species. Also, you are allowing a lot of calcium to go in. The cells were previously injured. They are looking for calciums. Now you gave the injured cells some more calcium. So what will it do? It will activate all those enzymes, and signaling pathways will again get haywire. Cell will be further damaged. Inflammatory cell, by allowing perfusion to be re-established, you are allowing leukocytes to go there, new leukocytes. So this will induce another bout of inflammation. And also the blood, the freshly perfused blood will have complements that can further damage the injured cells. So ischemia reperfusion injury is a real problem. Therefore, in any case where the perfusion needs to be re-established, especially in MI, the patient needs to be under very close supervision, and it has to be done very, very gradually. And the supporting measures has to be at hand. Science of initial improvement doesn't guarantee that the patient will become worse again. It really happened in many notable cases. Do you remember Mr. Ubaidul Kader was admitted in BSMMU with?
Yes.
Huh?
Yes, sir.
Yeah. So
Yes, sir.
yes, and he had MI. The perfusion was re-established to his myocardium. Things were going great, but suddenly his blood pressure really fallen to the ground. There was no pressure, no blood pressure for a few minutes. Okay, so it was due to this ischemia reperfusion injury. But however, he ultimately recovered, was transferred to abroad. But the
স্যার
management.
এটা কি
Huh?
স্যার এটা কি ইনফেকশন হয়ে যাওয়ার পরে নাকি ইস্কেমিয়া হওয়ার পরে?
Infarct tissue will not experience ischemia reperfusion injury to that extent.
মানে এটা জাস্ট স্যার ইস্কেমিয়া হওয়ার পরে?
Yes, the injured cells, mostly the injured cells maybe has not died yet. These are more prone to experience ischemia reperfusion injury, because if the cell is already dead, there is no point in calling it an injury. You cannot beat a dead person, can you? So you cannot further damage an already dead cell. So the cell has to be living to some extent for this thing to take effect. But it can also happen when infarct has progressed, because there are ischemic area adjacent to the infarcted area. Okay, but in old infarction, this thing will not happen. Now, what are the factors of cellular aging? We have already discussed this, and I'm going to skip these slides because this is not directly pertain into your subject matter under your curriculum. So I hope you are not bored to death yet, because there is other half of the lecture remaining, that is the cell death, which also comes with the injury. Are you okay? Some of you have got fallen out of the chair or something.
Yes, sir.
Huh?
It's okay, sir.
Okay, then let's continue. Now, the cell death, and again we look at the picture that remind ourselves that the journey from physiology to pathology is not some discrete steps. It's a continuous one. You cannot really pinpoint where one step ends and another step starts. So now, so far we have talked about from adaptation to reversible to irreversible injury, and now we will cover the last bit of it, the death. So there are different types of cell death. Let's start with necrosis. It's a type of cell death as the result of denaturation of intracellular proteins and enzymatic digestion of lethally injured cells. Please note that for necrosis, it has to be some enzymatic digestion. Where does the enzyme come from? Which enzyme? Can you remember from the previous slides?
Lysosomal enzyme.
Exactly. And lysosomal enzymes, the lysosomal membrane gets ruptured and comes out and activated by low pH and also with calcium. All those things, enzymatic degradation. Okay. Now, and the denaturation of intracellular proteins by these enzymes, not in normal cells, in lethally injured cells, because in normal cells, enzymatic degradation sometimes can denature intercellular proteins. We will see later. And also, can you give an example that if we just omit that lethally injured cell part here, it will not exactly be denoting necrosis. So can you think of an example that if you omit the last part, the lethally injured cell, the definition will be inappropriate? Can anyone guess why? Anyone? Okay, because enzymatic degradation of the intracellular proteins and denaturation ultimately causing cell death. There is a process, another process called autophagy. We'll come to that later. The cell doesn't have to be lethally injured for that. It can be stressed, but without being lethally injured, the autophagy can go about, and there are some other conditions where this type of enzymatic digestion can take place. So the part lethally injured cell is really important to keep in mind. Now, the histologic signs of necrosis, like there will be some inflammation. These are inflammatory cells, and we talked about pycnosis. Here you can see very dark nuclei here. There are other such nuclei here and there, but we're only pointing to the one of them. The cytoplasmic content is increased, and it's increased pinkish hue, and under hematoxyl eosin stain is called increased eosinophilia. And there are karyolysis. The nucleus is invisible. It's broken down into so small bits that it cannot be seen in light microscope. And there are some parts where you can see karyorexis, where nucleus is fragmented to smaller bits, but it can somewhat be visible, like these dark spots here and there. These are karyorexis. So these are some signs you can see under light microscope. Now, what are the main forms of necrosis? There are two basic forms, coagulative and liquefactive, and there are some special forms. Caseous fat necrosis, gangrenous fibrinoid necrosis, etc. Most common form of necrosis. Can anybody name the most common form of necrosis? Can anyone say?
Caseous necrosis, TB.
No, not exactly. Thank you. It's coagulative necrosis. Coagulative necrosis is the most common type of necrosis. Here, two organs are shown. This is a section of anyone. What is this section? Can anybody say?
Heart.
Exactly. It's heart, and it's showing an area of myocardial infarct. Okay, this white area. And can anybody recognize this organ?
Kidney.
This
Kidney.
Yes, this is this is renal infarct. You can see here, and the waist shaped necrosis is here because the circulation is renal circulation is maintained this way. If you follow the renal vasculature, it will follow this waist shaped pattern. So whenever there is some disruption of flow at this point, it will cause this waist shaped necrotic area. And what about coagulative necrosis? So this is actually not a coagulative necrosis. This is sorry, this is a coagulative necrosis, and this is from myocardium. You can see that in coagulative necrosis, the overall structures of the cells, the myocytes, are preserved. You can still recognize them as myofibrillary type, like they are strong, they're long strands, tubular forms. When they were alive, this form, they had this form, but now they're dead. How can you say that they're dead? Can anyone say these are inflammatory cells inside? These are leukocytes, WBCs in between the microbial stands. But does the cell themselves have any nuclei in them? The dark pointy thing that we saw before. In any
No
case,
nucleus.
huh?
So nucleus 9.
Exactly. So, but the structure, cellular structure is there, but the nucleus is not there. Okay, and also some dark patterns are here. The eosinophilic, these contraction bands, they're known as contraction bands, these bands. So all these things indicate that this is a coagulative necrosis. Why coagulative? Because it's the proteins sort of coagulate at their places. They clump at their places. They do not spread out. They are not liquefied. They kind of remain solid. So it's called coagulative necrosis. They maintain their structures. So as we can see here, this is also another example from kidney coagulative necrosis, where there is a normal area and there is a coagulative necrosis area. So can anyone say there are 2 points here? One is square and is circle. So which is which? Which denotes normal area and which denotes coagulative necrosis?
So I think upper part is coagulative necrosis, rounded question mark.
Rounded portion is coagulative.
Coagulative.
Exactly. Thank you. So and can anyone recognize this structure, this round structure here? I'm hovering my pointer over.
Glomerulus.
Glomerulus.
Exactly.
Glomerulus.
This
Glomerulus.
is a glomerulus, and these are tubules. These are also tubules, but they're dead. Okay. Coagulative necrosis. Okay, and these are alive tubules. I mean, when the slides were prepared, all of them are dead. But I'm talking about the point when the sample was taken. So you get what I mean, right? Huh?
Yes, sir.
Okay. So sometimes do you hear this kind of things, that this fish was fresh live fish from Padma, fresh live Hilsa fish from Padma. So things like that. When you're eating the fish is no longer alive, but it means that it was caught fresh from Padma. So when I say dead, I mean that at the point of collection of the sample, not that when the slides are prepared. Okay, so I think it's obvious to you by now. Now, what is liquefactive necrosis? So, in is an example from brain, and in brain we do not see coagulative necrosis. That's an interesting thing. In brain, necrosis always comes in liquefactive form, and if there is tuberculosis, then we can get sometimes caseation, but we do not get the actual coagulative form of necrosis there. In brain tissues, the structure is not preserved. It's like smeared, it's liquefied. The dead cells contents are spread over, and it's no longer visible as distinct structures resembling its living counterpart. You cannot differentiate the cellular outlines or margins like we did before. As you can see here, this area inside this area pointing towards these arrows point toward the area of liquefactive necrosis. There are inflammatory cells there, but other than that, no structure is appreciable here. And the surrounding area, these are inflamed somewhat, but they're still alive. There are other examples like in liver abscess. So can anyone say that which side of it is coagulative, liquefactive necrosis, the right part or the left part?
Sir, right, sir.
Right part. No, I don't think so. You see that there are strands. I mean, liver cells, structure of the liver cells and trabeculae are intact on the right side.
Oh, yes, 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 yes.
Huh?
Yes, sir.
Yes. So there are some necrosis, but on right side, whatever the part is necrosis, something on the right side, if there is necrosis, it has to be coagulative necrosis. But on the left, we see
Yes, sir.
liquefactive necrosis.
No structure.
Yes. Huh?
So structure is
Mr.
missed over.
There is no discernible structure. It's like
Yes, sir.
one big pond has different types of fish in it. There is
Yes,
no
sir.
particular fish you can identify in isolation. It's like a big smeared thing. That is liquefactive necrosis. Yet another example here, liver abscess. The arrow points to the area of liquefactive necrosis, and there are leukocytes. I mean, WBCs are surrounding it. It's necrosis always comes with inflammation. This is necrosis is always accompanied by inflammation. Inflammation means inflammatory cells and things. Now, caseous necrosis. Here, an example from lung is shown. We see the typical cavitation of that points towards the possibility of tuberculosis here, and the caseous and this is a lung tissue collected from the patient, and uh, this is the microscopic view of caseous necrosis. So we do not go into the detail right now. Just to let you know that tuberculosis is one of the uh, one of the reasons, one of the etiologies behind the caseous necrosis. And whenever the necrosis is caseous, it is usually suggestive of tuberculosis. So that's, and this is how it looks like. It's pinkish and kind of granular, and there are other features, but the magnification is not enough to show you all the cells that are in here. Just look at the big picture here, and also appreciate the giant cell you can see here. Now, the fat necrosis, this is actually from peripancreatic tissue, the mental fat necrosis. And in fat necrosis is actually, the fat necrosis is not exactly a necrosis. I mean, what happens is that fat cells, they have got triglycerides in them, right? The fat cells contain triglycerides. Everyone agrees that, right? Do you agree with me?
Yes, sir.
Okay. Now, sometimes that fat cell is injured by uh, enzyme, I mean pancreatic enzyme, and sometimes it can be traumatic, like commonly in breast lesions. So these things, this stress or this injurious stimuli sometimes ruptures the adipocyte, and the fat content is spilled outside. Now, our immune system, do they have the familiarity of this exposed triglycerides? Normally, does our immune system come into exposure, directly come into exposure with uh, triglycerides and free fatty acids? Do they directly come into exposure? Not free fatty acid, triglycerides. Our immune system.
No, sir. Immune system এর সাথে তো triglyceride
Yes. So immune system does not know how triglyceride looks like. Okay. Because whenever the triglyceride is transported within our body, it is transported within what? From in the circulation, the triglyceride is transported, right? Through what? Through triglycerides are transported via
Chylomicron.
exactly, chylomicron and other
VLDL, VLDL.
Okay. So the uh, free triglyceride is normally does not come into contact with immune system. Okay. So immune system to the immune system, the triglyceride is foreign substance. Do you understand? Do you get this point?
Yes, sir.
Okay, so when the adipocytes are ruptured and the triglyceride is spilled into the surrounding tissue, there is inflammation. Okay, so and it causes some inflammatory changes around that fatty tissue. So that is called fat necrosis. Okay, it is not exactly like the other necrosis where the cell, gets injured. There are lots of steps and everything. The adipocyte uh, may or may not die because uh, even after spilling some of its materials, the adipocyte can heal itself. Okay, the adipocytes are very hard to kill. Those of us who have gained some weight and trying to lose it, we know it very well that getting rid of adipocyte, killing them is very difficult. Do you agree? Huh?
So difficult, sir.
Yes, it's very difficult. So the adipocyte doesn't have to really die. Some of its triglyceride has to spill out or something like that. Then it will cause some reaction, and it's called fat necrosis, although it's not typical necrosis. So here the some adipocytic contents are released here, and the inflammatory reaction is shown by the star mark here. And some ghost cells are there. That is the vacuolated or vacated adipocytes. I mean, the ghost of adipocyte, in some sense. I know the scientist who named it had a, I don't know, had a terrible sense of humor. Called it ghost cells. Okay, now the fibrinoid necrosis. And fibrinoid necrosis is also not really a necrosis. When do you remember type 3 hypersensitivity? Anyone can tell me what is type 3 hypersensitivity? Please.
So antigen antibody complex mediated.
Yes,
Yeah.
antigen antibody complex deposition associated hypersensitivity. Okay. So sometimes the blood vessels has got antigen antibody complex deposition within its wall, and that under microscope looks like this. This is a blood vessel, and normally the blood vessel wall should not be eosinophilic and homogeneous and glassy appearance. It's not like that. But what you see here is fibrinoid necrosis. It's usually due to type 3 hypersensitivity that also associates with vasculitis. It is commonly seen in different autoimmune conditions like SLE. And uh, so we have covered almost half of the of this cell death portion. So could you follow me till now, because we are almost at the end of our lecture.
Yes, sir.
Okay, so now comes the apoptosis. Some of us pronounce it as apoptosis, but the pronunciation includes a silent p. The second p is silent, so actual pronunciation is apoptosis. Okay. Can anyone know what ptosis means? Ptosis, P-T-O-S-I-S. Familiar with the term?
No, sir.
Huh?
No, sir.
Ptosis of eyelids. Anyone?
Yes, drooping of eyelid archy. Yeah.
Exactly. So ptosis comes from Greek, Latin, I don't know, word which means falling of leaf. Okay, like in winter, the winter is coming, so uh, some of the trees are going to lose their leaves. the leaves will silently become yellow and drop off from the tree to the ground. So the process of dropping a leaf is called tossis. Okay, so the eyelid is compared to the leaf, it's drooping, so it's called tossis, and the cells are silently dying peacefully. So this is called apoptosis, also compared to the falling of leaves from trees. Okay, we have seen that uh, uh, necrosis is a messy process. Uh, the cell is burst open, there is inflammation, there is tissue involvement, and lots of nasty things. But in apoptosis, the cell dies alone. It doesn't cause harm to other cells. It's, uh, it's like a leaf silently falling off a tree uh, without causing any further damage. It's like that. Now, the pathway of cell death is induced by tightly regulated suicide program, and it activates intrinsic enzymes that degrade its own DNA and nuclear and cytoplasmic proteins. But this degradation is not like necrosis, it's a very systematic. Now, how apoptosis is initiated? There are two ways of apoptosis. One is the mitochondrial or intrinsic pathway, and other is death receptor or extrinsic pathway. Now, the mitochondrial or intrinsic pathway, the signal comes from the inside. I mean, if there is no growth factor is working, growth factor is withdrawn, the DNA is damaged in some way, or protein is misfolded. In other words, the cell is not fit for another cycle of cell division. If the cell divides, it will cause some problem. It can cause cancer cell, it can cause malignant transformation, it can cause some functional disruption. So in that case, the cell just quietly die, because if it keeps on living, then it might cause problem. So this is mitochondrial or intrinsic pathway. The inner abnormalities of the cell is triggering a suicide pathway, that is intrinsic pathway. And there can be extrinsic pathway, like signal coming from outside. Can anyone give an example of an extrinsic pathway signaling where some outside agent is asking the cell to die quietly and peacefully? Anyone? Can anyone give an example of that? Okay, one common example is like in viral illnesses. If the cell has got viral load inside it, it has got some surface markers to identify that, and immune system can recognize that. And natural killer cells can often signal that virus embedded cells, virus infected cells to uh, switch on its apoptotic program. In that way, the cell dies, but it takes with us millions of virus. So this suicide is actually beneficial. And sometimes the immune mediated death response is there, extrinsic pathway response. Like if there is a lymphocyte that reacts to self antigen. So if a lymphocyte keeps living, which can react to self antigen, is it good or bad? If a lymphocyte can detect and react to self antigen, is it good or bad? Anyone? Hello?
Bad.
Yeah, why it is bad? Because why a lymphocyte that can react to self antigen bad?
It will damage his own cell.
Exactly. So that cell has to die, right? If it,
Yes.
so that signal is also come from extrinsic pathway. Okay. So these are some examples of extrinsic pathway, and intrinsic pathways are those where the internal machinery of the cell is somewhat damaged, and if the cell continues to live or continues to proliferate, then it may cause further damage, like it may cause cancer or it may cause something that's not desirable. In that case, intrinsic pathway is activated. The two main pathways, extrinsic and intrinsic. So the two ways to initiate the apoptotic pathway, but it ends the same way. At the end, you will see some the cellular contents are packaged into small vacuolated structures, which are called apoptotic body. The apoptotic body contains a bit of nucleus, a bit of endoplasmic reticulum, a few mitochondria. It's like small piecemeal things, like the cell is broken down into small pieces, but the intercellular content is not released into extracellular space. They are bound by cytoplasmic membrane. So the contents are not released. So inflammation is not triggered because the contents are not released. And these are quietly taken up by the macrophages. Okay, this is how the apoptotic pathway ends. It can begin by intrinsic or extrinsic signal, but ends the same way. Now, this is the basic differences. We have already talked about it. Differences between necrosis and apoptosis. Necrosis is a very messy process. The cell breaks down, inflammation is there, cellular contents is leaked outside. The immune system is not familiar with cytoplasmic content. It thinks that it's foreign, so it attacks and therefore inflammation. But in apoptosis, the thing is very controlled. The cells disintegrates into smaller bits enclosed within membranes. So the immune system does not get in contact with the cytoplasmic material. Inflammation is not induced, and phagocytes can take up quietly those apoptotic bodies. So these are the basic differences between necrosis and apoptosis. And we have already talked about this. In apoptosis, the cell size is usually reduced. I mean, not like the hydropic changes we see in typical necrotic injury. And all other differences has already been discussed as given in this table. Now, apoptosis has got a lot of physiological role. One of the example is shown here. During embryogenesis, the finger formation, the limb bud causes the finger buds to form, the digital buds to form. And initially, there are some connection between the developing fingers. Like, have you seen the feet of ducks? Duck feet? Have you seen duck feet? Anyone?
Yes, sir.
They have got webbed feet. Their digits or fingers are connected with one another by a connective web. Have you seen that?
Yes, sir. Flapping
Yes. So
connected there.
exactly. So similar things are happening when embryo is developing. You see here, and these connected cells at some point dies by apoptosis, by programmed cell death. And if it somehow fails to occur, then we get this syndactyly. Okay. And apoptosis can also be induced by viruses. You can see in viral hepatitis and some other conditions. And another example is HIV. It causes apoptosis of CD4 positive cells, which is, by the way, bad for us, because without CD4 cells, the immune system is destroyed. Now, we have already talked about a physiological role. So can anyone say that how does the immune system make sure that the lymphocytes do not react to its self antigens?
By keeping memory cell, through memory cell.
No, memory cell is actually something that prepares the body for future attack of the same antigen. It can mount immediate and intense response without waiting for all the steps of primary infection. So memory cell is about you have got an infection, and if you get it second time, memory cell will come into action rapidly. So that's not the case here. I'm talking about the phenomena where our self-reacting lymphocytes are destroyed. Our self-reacting lymphocytes get killed before it causes some autoimmune reaction. So how does it do that? Normally, we do not we are not autoimmune. Are you all patient of autoimmune disease? What do you think? Does everyone get autoimmunity? No, right? Only some of them do. Those who have autoimmunity has some kind of reaction to their own antigens, and there are lymphocytes that can act against their own antigens. But normally this does not happen. Why? Can anyone say? Anyone? Hello.
No, sir.
Okay.
Cannot remember.
Okay, so let me explain. Do you understand the question? The thing is that, do you understand the question? Huh? Okay.
Yes, sir.
Okay. So the thing is that the uh, these self-reacting lymphocytes, they get identified by other immune cells, and these cells get an extrinsic or apoptotic signal, and they commit suicide before reacting to any self-antigen. Okay, though they undergo apoptosis. If some cell can react to self-antigen, the instructions are given that you commit suicide, and that cell commits suicide before causing any further damage. Okay, do you understand now? Huh?
Sir, I have to
Okay.
elaborate.
Okay, so self-reacting cells get self-reacting cells, reacting T lymphocytes or lymphocytes get extrinsic apoptotic signal, uh, and so they commit suicide. Those lymphocytes that can react to self-antigens will commit suicide via apoptosis. That's why normally our cells do not react to our own antigens. Okay?
Okay, sir. Got it.
Huh? Got it? Got it now?
Yes, sir.
Okay. Now the thing is that this apoptotic, uh, yeah, this apoptosis can be prevented by some genes. Like BCL2 is a gene. BCL2 is a gene that can inhibit apoptosis. Okay, BCL2 is an anti-apoptotic gene. If it is active, then apoptosis will not occur. So this lymphocytic education, where lymphocyte dies if it reacts to self antigen. So these things happen in many places within lymphoid system. One of the places is the follicles of lymphoid, the lymphoid follicles. The lymphoid follicles in the left hand picture here, you see this pale round area here. You see this pale round area here.
Yes, sir.
So these are lymphoid follicles, and within this lymphoid follicle, this apoptosis is taking place, where in this pale round area, the lymphocytes which uh, get uh, which can react with self antigen, they undergo apoptosis and they die in these areas. Okay, these are the places where the lymphocytes are selected, so that they are not they do not react with self antigen. And uh, this is hematoxylin eosin stain, and this is immunostain. This identifies a protein called BCL2. This brown color, wherever there is a brown color, the BCL2 protein is active, and if it is pale like this, the BCL2 protein is inactive. So when BCL2 protein is active, the cell is anti-apoptotic. The cell does not die. Okay. If the BCL2 protein is active, the apoptosis cannot occur. Do you get this point?
Yes, sir.
Okay. Now, the BCL2 protein is active inside this follicle. These and these are the same things, just stained in a different way. So that's from the same area. These two sections are taken. Now, as you can see, within this follicle, the BCL2 is active or inactive here, expressed or not expressed.
Sir, active.
No, it's not expressed. If it is expressed, then it's more brown color. It's less brown, it's pale area. Pale area means the protein is not there. Okay. And there are many tiny lymphocytes you can see. None of them has BCL2 expressed within them, but the surrounding area has got BCL2. You see, darker. The lymphocytes that are in this region has got BCL2 expression, but within this region, the lymphocytes, they do not have BCL2 expression. In this area, a lot of suicide is going on, a lot of apoptosis is going on. If BCL2 is activated within this region, then the cells will not die and the self-reacting lymphocytes will survive. Okay, so that will be a disaster. So here the BCL2 expression is off. That's why immunohistochemically it's stained pale. But once the cells are selected, which cells will die, which will survive, everything is sorted out, the cells moves to the periphery. So here the anti-apoptotic genes are again active. This BCL2 is again active. So the selection is done. It is decided who will live and who will die. And after that, the BCL2 expression is there. So the thing is the normal process. In the center of the follicles, the lymphocytes that react to self-antigens die, and then those do not react to it do not die, and ultimately they are they moves into the periphery and ultimately into the immune system. So this is the normal process. Once the suicide program is done, after that the BCL2 expression is again there, because we do not want these trained lymphocytes to die prematurely before fighting their fight. But what happens in case of follicular lymphoma? In that case, the suicide program is actually dysregulated. The BCL2 protein is expressed where it should not have been expressed. So in follicular lymphoma, we see that BCL2 expression is there. That means the cells are not dying, and it causes lymphoma. It can also cause autoimmune conditions and also cause many other problems. If something that was supposed to commit suicide does not commit suicide in our body, then the body has to suffer for it. I don't know, maybe this was a bit of complicated example, but it's in the book, so I think I should mention it. If you do not understand it properly, don't worry, just forget it. But those of you have got it, I think you found it interesting, I guess. Now, can anyone say that what is the main difference from apoptosis and necrosis? Anyone?
Apoptosis, there is no necrosis.
Apoptosis, there is a disaster হবে না, silently hello.
Apoptosis mainly sir is not pathological, mainly non-pathological, but necroptosis may be pathological.
Okay, the thing is that apoptosis and necrosis, necroptosis is in between apoptosis and necrosis.
Yes, sir.
You can think of it like this way. If
start as a হচ্ছে স্যার হচ্ছে necrosis and end as a apoptosis, sir, something like that.
Yeah, it is something like that. The thing is that necroptosis is an example. Actually, in reality, we do not usually get a pure apoptosis. It's very rare. Pure necrosis is also not that much common. The thing is that whether it will undergo apoptosis or necrosis is ultimately decided on the severity and the timing of the stimuli. The cell by default tries to commit suicide, tries to undergo apoptosis, but sometimes there is a injury so severe that it doesn't have to have time to complete all the necessary programs to complete this silent death. So in that case, the cell dies through necrosis. So thing is that if the injury is intense, it usually undergoes towards the necrotic spectrum, and if there is enough time to regulate everything and introduce the stepwise pathways, it will undergo apoptosis. and apoptosis costs energy. It's an energy consuming process. So apoptosis cannot happen when there is some sort of energy shortage, like in hypoxia or something. Okay, so by default, cell tries to die peacefully. Okay, but when it cannot, it undergoes necrosis. And when it sort of goes in between the two, then it's necroptosis. This is the basic idea. Do you get the point now? Huh?
Yes, sir.
And one difference between apoptosis and necrosis is caspase 8. So what is that? It's an enzyme where the apoptotic pathway is initiated, but at some point the caspase 8 could not be activated somehow. So if the caspase 8 cannot be activated, the cell dies like necrosis, although it started as apoptosis. So this is cell death by necroptosis. And if there is activation of caspase 8, then it's well and good. The cell death by apoptosis is accomplished. Uh, and there are a lot of steps between the failure to activation of caspase 8 and cell death, which is actually shown here. The steps in between failure to activate caspase 8 and cell death by necroptosis, the intermediate steps are like this. You can look at it, but basic idea is that it doesn't have enough time to regulate all the steps, and the key steps that differentiate between apoptosis and necroptosis is a step with the caspase 8. If it fails to activate in time, the cell starts by apoptosis and dies by necrosis. That means necroptosis. But if the caspase 8 can be activated in time, the thing starts as apoptosis and also ends as apoptosis. Now, there are some other types of cell death that has been recognized later. One is pyroptosis. I'll not discuss in detail about this. This is something that related to severe inflammatory response. The pathway mechanisms are a little bit of different than the necrosis, apoptosis, or necroptosis. So basically, it's a form of severe inflammation. We talk about these cytokine storms nowadays. Are you familiar with the term? Have you heard the term cytokine storm in relation to this COVID-19?
Yes, sir.
So in this case, the severe autoinflammatory responses, cell death occurs via pyroptosis. So I'll not go into detail about this already, we are past time. So, and there is autophagy. It's something that the cell eats its own contents. It happens under severe stress, severe stressful condition, and also associated with some diseases. In some cancers, the autophagy is beneficial. In some other cancers, the autophagy is harmful. In some neurodegenerative conditions like Alzheimer's and some autoimmune conditions like inflammatory bowel disease, all these things has got something to do with autophagy, and regulation of autophagic pathway happens to keep protection against some microorganisms as well. So autophagy is involved in a lot of processes. For this, the mechanism of autophagy was awarded a Nobel Prize in 2016, I think. Can anyone, if I'm saying this wrong, please correct me. The mechanisms of autophagy was awarded a Nobel Prize in Physiology or Medicine in 2016, possibly.
So Japanese একজন পেয়েছিলেন।
Yes. The thing is that I'll just, you already have learned about autophagy, something, the cell eating itself under stress. Okay. It's like it's not getting anything to eat, so it's eating itself. It's something like that. But mostly it's not about starvation. This is a widespread misconception that starvation causes autophagy. Yes, it's true. Starvation can induce autophagy, but that is not the main importance here. The main importance is clinical. It is associated with many neurological, degenerative, infectious, and neoplastic processes. So there can be therapeutic targets. So this is the importance of autophagy. There are lots of, I've read internet, on the internet, some articles like claiming the benefits of starvation through autophagy. But all these things are quite nonsense. Because the starvation gives benefit, starvation is beneficial. I'm not saying that starvation will not make you healthier. Starvation to some extent is good. I agree with that. But in humans, the starvation, the benefit of starvation is not derived via the autophagic pathway. That is the thing. In humans, the starvation gives us some benefit. If we take lower calories, then it benefits us and helps us live a longer life. That is true. I do not deny that. But I am denying the fact that some internal articles are there, which is claiming that in humans, if you take low calorie, the benefit is derived via autophagic pathway, but that is not the case. It is found in worms, that is elegant worms. It is found in starvation-related longevity, is also found in rats. But in humans, there is no evidence that autophagy derives starvation-associated benefit. If you take low calorie, you will have some health benefit, but that is not via autophagy. That is via other pathway. In human, it is only relevant in some clinical contexts, like in some diseases I just mentioned. So, do you understand this point? What I said?
Yes, sir.
Huh?
Yes, sir.
Okay. Now, these autophagic steps are shown here. It's basically cell contents are packaged into small vacuoles, and ultimately lysosomal degradation is there. After that, the cell can use these components again. But you know, eating eating the own machinery of the cells is not a very sustainable process. Ultimately, cell dies if it keeps doing that. Now, these are the key differences between different types of cell death: apoptosis, pyroptosis, necroptosis, and necrosis. You can go through it later when I forward it to you. It's like a very very shortcut chart for you to go through. And this is another diagram that shows apoptosis, autophagy, oncosis. Oncosis basically cell swelling. Oncosis, the term oncosis, onco means swelling. Oncosis, cell swelling, and then necrosis. And pyroptosis, all these things are shown also here, showing here. The dying cells, it means irreversible cell injury, and dead cell is actually cell death. So you can also go through it. It's a summary of what we have discussed here. And now lastly, any questions or comments or anything? Questions or
স্যার
comments?
আগের স্লাইডটা স্যার যেটা স্যার ডিফারেন্সটা ডিফারেন্স
হ্যাঁ
ছিল স্যার হ্যাঁ এটা একটু স্যার
হ্যাঁ sure. No need to.
সেল লাইস
স্যার থাইরয়েড ফলিকুলার কার্সিনোমা আর ওই যে ফলিকুলার লিম্ফোমা যেটা, এটা কি প্যাটার্নটা কি একই?
No, follicular carcinoma. Follicle means some round structure. Round structure. Any round structure called follicle. Okay, it can be normal, it can be abnormal, it can be tumorous, it can be non-tumorous, whatever. So thyroid, in thyroid, if the tumor cells are arranged in like round structures, this is that is then the term follicular carcinoma or follicular pattern is used. And uh, in case of follicular lymphoma, the lymphoid organs like lymph nodes that can have these round ball-like structures, follicles. Follicle means something round and ball-like structure. So the similarity is only on the superficial, on the overall shape of the arrangement of the tumor cells. Other than that, there is not much similarity. Only the shape is like a follicle or round, something round. There are, I mean, follicles. The term follicle is not exclusive to cancers only. We use the term follicle all the time, like Graafian follicle. Anything that is something round, enclosed, ball-like structure, anything like that, we call it follicle. So only the arrangement is similar here. The cells, the genetic programming, the outcome, the prognosis, everything is different. Only the morphological pattern is follicle, looks like follicle. Other than that, there is not much similarity between the follicular carcinoma of thyroid and follicular lymphoma. Okay. So any other question, comment, or anything? I'm already actually we're running late. So
Sir, one question, sir. You said earlier about pyroptosis. In COVID, sir, pyroptosis can happen in COVID situation.
yes, it can. It happens. The cell death in cytokine storms is ultimately caused by pyroptosis, pyroptotic pathway. The hyperinflammatory reactions, that is the end state of a cellular level, the end stage of cellular level in case of cytokine storm, the cell dies through pyroptosis.
Oh, okay, sir.
But the virus-mediated cell death is not pyroptosis. It's the overreaction of the inflammatory mechanism that causes pyroptosis. Okay. Okay, so I think we can conclude, and hopefully we will meet again on next class. And the next class is really very, very vast topic. I mean, atherosclerosis and